Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
I'm a little bit hesitant to start talking for a seminar on mathematical consciousness because there would be very little mathematics in the talk and even less about consciousness. So I hope you bear with me, and I hope you see that there are still some connections to consciousness in my general philosophical problem here. So the problem is how to describe the structure of cognition. I use the word cognition, not consciousness, but there are, of course, connections here. And my problem is really we can call it the neo-Kantian problem. What are the fundamental categories of our thinking? When Kant said it was time and space and causality and a few more things, I go for a different type of answer, but it's still the same kind of problem. And the problem is well described by William James in his book on 1900 book, I think it is, where he says that the baby, the newborn human being, is faced with a blooming, buzzing confusion. I like that expression very much. And then somehow the baby learns to organize that confusion into what he says one and the same space. And I take a little bit of issue with his idea about one and the same space, but still the idea is that we make sense out of all the very complicated information that hits our senses. And the question is, what happens when we make sense of them? And I describe that as we have these sensations. That's what hits our senses. And then they're reduced to perceptions, where we have organized the world into objects and so on. And my idea is that the brain looks for invariants in what hits the senses. And what I want to do is to try to say something about how these invariants look like and what their purpose is. And I take a starting point in the work of two child psychologists, Elizabeth Spelke and Susan Carey. And they have argued that there are in the child four basic core, what they call core categories: space, objects, actions, and numbers. So these will be the categories I would like to analyze. And my basic question is, why these categories? Why do our brains organize the world in space, objects, actions, and so on? What is the reason for that? And the basic reason, okay, I should say first that they are nativists. That is, that they think that the baby's brain is made for using these structures. I don't quite agree with them. I mean, I think that the brain learns to find these categories. Not totally. I'll say a bit more about that later. So I'm more of an empiricist, that we learn to identify these invariants that generate the basic categories, what they call the core categories. So I want to use this notion of invariance. I mean, for a mathematician, this is fairly trivial. And what I want to claim here is that these categories can be characterized by their invariances. I will do no formal mathematics here, but I still want to say something about how we could go about and developing maybe a slightly more mathematical theory built on invariances. I'm a bit preposterous to say that this can be seen as an extension of the Erlangen program. And the Erlangen program, where you try to define algebraic structures in terms of invariances. Here I try to identify cognitive structures in terms of invariances. But the main difference is that I do this very informally, and I'm not sure I can turn it into any form of proper mathematics. But the idea is basically the same, that we have these structures, we can identify them via a set of invariances. So that's the fundamental idea. And You can also take some starting points from J.J. Gibson, who says that we don't have to construct an awareness. We just have to detect their invariance in the world. And here I take a little bit of issue with Gibson because he is an externalist. He thinks that the invariances are out there. I think that the invariances are construed by the brain. So my position is a little bit different from Gibson's, but still the idea is the same. The world has its invariances. We have to pick them up. I already said this. And then, of course, the brain has adjusted slowly over evolution to find the best sets of invariances that finds the best organization of how we perceive the world, that helps us best act and survive in the world. So there is some kind of evolutionary grounding to these structures. We could, of course, imagine some kind of weird science fiction world where organism's mind, if you like, don't sort the world up in spaces or objects and actions and so on. But it's difficult for us to think about that. Our brains are really made for seeing the world in these categories. So, and the concept I will use quite often here is called fungibility, and officially defined as replacements of equivalence. This is something that economists use, but I will use it in a different way. So the idea is that any bag of corn grade 2 of 10 kilos, say, can be exchanged for another bag of corn grade of 10 kilos. Economically, they are identical. Or a $2 bill can be exchanged for two $1 bills. They are totally equivalent. We can change them without losing or gaining anything. So that's the notion of fungibility. Now, this is a very simple observation, but objects are fungible with respect to places. If you have a place and you move objects around, you put new objects there and take away objects, then the place remains the same. That's one kind of fungibility. And similarly, if you have an object and if you move it around between different places, it's still the same object. There are two kinds of fungibility here that are part of what's invariant in the characterization of places and objects. Actually, the notion of fungibility will be most important for me when I analyze numbers. So let me now do this was my introduction. Let me now do each of these three categories: space, object, and action. And then I wrote a paper a year ago, or published it a year ago, about these three types. And then the fourth category, number, is something I'm working on at the moment together with a colleague, Paula Kinnon. So that part is still work in progress. So let's start with space. When we learn to perceive space, I mean, we are not born with a space perception, but we learn it. And one can make a distinction between different kinds of perceptual spaces. One area is what's called peripersonal space. And that's basically how far you can reach with your arms, or how far you could reach with your arms and a stick if you have two. We have this perception which is made for us to act in. The second is extrapersonal space. That's what you see. You see the world around you. And that's, of course, to keep track of enemies and dangers, and for navigating in your world. But it can be shown that these are partly handled by different regions in the brain, and different neurons are involved. But they are somehow joined together. And then finally, we have this allocentric space, where we can, I think there is something behind me, even if I have no perception of it. I have some kind of image of the full space. I mean, I live in Lund, and I can imagine walking around in Lund. I can imagine traveling to Denmark and Germany and so on. And I can use that for planning. And this allocentric space is handled by the hippocampus. I mean, that's one of the major roles of hippocampus to help us in finding our ways around the world. And yeah, space representation is not innate. We develop from the personal space. I mean, the first thing that happens to a baby is that they learn to coordinate hand and vision. They learn to reach their hands to where they what they are looking at, and so on. So they have this from the beginning blooming, buzzing confusion, and then they end up with structuring the space and knowing how to move the hands to reach particular positions in the personal space. And then when they start moving, it's extended to an extra personal space. And then even later, they can start imagining places in the space that they're not perceiving. So there, we see a development in the child's space cognition in these steps. And one example of that is it's an experiment that Piaget made. It's called the 3-mountain task. You put a child in front of 3 toy mountains, and then there is this teddy bear at the back, and then you ask, what could the teddy bear see the house? And the small children say, of course, because the child can see the house, but they can't imagine the world from the viewpoint of the teddy bear. So that means that I still haven't got the full access to the heliocentric space where they can imagine being at another position and how the world would look like from that position. This is just one example of that our space perception is developing over time. But I mean, I'm assuming that we talk about this allocentric space in the sequence. So now that's space perception. Let me get into how we find invariances in space. And for a mathematician, this is all well known, but I'm connecting this to a little bit to cognition here. So the extra personal space is invariant of eye and head position. So if I turn my head and turn my eyes, the world still stays still. So it doesn't move. That means it's our construction of the extra personal space has these invariants. But allocentric space is also invariant. I mean, I still imagine the positions within Lund or within Europe as being invariant, or where I am, or in which way I'm turning. So we have more invariances for the allocentric space than we have for the extra personal space. Yeah, Gibson says that this is we learn to isolating what remains invariant during these transformations. He's almost only concerned with visual invariance, but I think that my argument applies to other invariants as well. I mean, we learn to connect our hearing and to some extent our touch to the perception of space, and we connect. I mean, I can feel my way around in the room and make up an image of how the room looks like by only using my hands and, of course, my own locomotion here. And trivially, ordinary space is invariant under Galilean transformation, that is rotations and translations, and also invariant of time. So even if time moves, the space normally stays the same. So that's these are the Galilean transformations. And as I said earlier, I mean, I already introduced this idea that the space is invariant of the location of objects. We don't think space changes if the objects move. There are some interesting things in animal cognition, but I don't want to get into that here, maybe later. And then we use space to, we can say we create concepts on this space domain. And these concepts we can call places. They are regions of space. And these regions, I mean, I said that space is independent of objects. But in general, we have landmarks, the sea, a mountain, a forest, something that determines the location of a place. So that means that the location is not totally independent of objects, but basically, I mean, these landmarks are things that we don't move around. I mean, seas and lakes and mountains, we don't, forests, they don't move very quickly, so we can use them as landmarks. So this is it's kind of categorization of space is places. That's all I have to say about space. I mean, it's nothing very sensational here. The idea is that that's characterized by the Galilean transformations, and yeah, mathematically not very much else. Then next topic is object. And now object invariances become more complicated. There is no unique set of invariances for objects, but there is a hierarchy of different kinds of objects. Again, objects are invariant under Galilean transformation. If I rotate the glass, if I translate it, if it changes in time and so on, it still remains the same object. But we have other things here. Oh, by the way, this constancy over time, that an object doesn't change over time. Of course, some objects do, but in general, the existence of an object is maintained over certain periods of time. That connects to what, again, Piaget calls object permanence. And that manifests itself in that children, if we hide something under a pillow, children above, I think it's 9 months, they will look for the thing under the pillow because they still have a representation of the object being there, while younger infants don't think that the object, or don't react to the object being out of sight. It doesn't exist for them anymore. But once you get this object permanence, you assume that the object has a location in space-time. And if an object suddenly moves from one place to another, you will be extremely surprised. I mean, there has to be some kind of spatial-temporal continuity in the changes of locations of objects. So magicians are good at fooling us on that, but that's another story. Well, the objects in general, I mean, when I talk about physical objects, they have a shape. Now, the shape can be more or less invariant. So if we talk about rigid objects, even if I move a rigid object in space, rotate it, translate it, and so on, the locations between the parts, the relative locations, the distances between the parts of the object remain invariant. So that's one form of invariance that holds for rigid objects, that the distances between the objects. And actually, our cognition uses that quite extensively. We can compare it to objects with movable parts, like humans and animals and some machines, like cars or trains and so on. The parts can move in relation to another, but the positions within a part, within my lower arm or within the wheel of a car or whatever, they remain constant. And furthermore, the connections between the body parts and so on, the connection places also remain invariant. So even if it doesn't have as many invariants as rigid objects, the objects with movable parts still has a fair amount of invariances that we use. And Swedish psychologist Gunnar Johansson called this the rigidity principle. If I move my arm and if I see two dots moving, I presume that the distance between the two dots is constant in 3D. And that helps our perception. We can very easily see the movements of humans and other things by assuming this rigidity principle. So that's a kind of invariant for many objects, not for all objects. And if you have read David Marr's book on vision, he uses this principle very strongly in his algorithms for identifying shapes, the so-called rigidity principle. So that's been used in computational work about identifying objects. And also, if you have a rigid object or an object with movable parts, the size of the object is often invariant. And that helps us in judging distance to objects. We have this phenomenon called size invariance, where we can see the distance to an object by judging its size on the retina. And but we still assume we see the object as having the same size. This size invariance it takes place very early in the visual process. I mean, the information from the retina hits V1 in the back of our skulls, and then it's produced, projected forwards, and already in the area 3, we start picking up these size invariances of objects. So that is a very early part of the visual process. Now, there are also other objects that are not so nice. We can have deformable objects. I only have two examples here, towels and doughs. There, the parts, the relative distances between the parts change when you fold a towel or you knead a dough or whatever you do. The invariances are much fewer. On the other hand, we still have continuous changes between the parts of the objects. Unless the object breaks, it still hangs together. There's a kind of cohesiveness in objects. And if you talk about masses like water or air or sand, there is no continuity in its changes. I mean, mass of water can change its location without continuous continuity being the holding. So there is a difference between an object, even if it's deformable, and masses in this respect. It lacks masses typically lack continuity. And also, I already said that objects are cohesive. And that means that some objects are a little bit marginal. I mean, if you take a cloud in the sky, it looks cohesive, it looks like it hangs together, but it's a cloud can very easily break up, or two clouds can join, we see it as an object, but it's marginal. Or a shadow. I mean, we talk about shadows, but they are not really objects because they don't have this continuity. If you move the movement of a shadow, it will might be quite often non-continuous. So what I'm saying here is that we have different classes of objects. The class with the largest class of invariances are the rigid objects, and then comes the objects with movable parts, and then we have the deformable objects. But they still have some invariance. I mean, like continuous movements and cohesiveness. So the situation for objects is a little bit more complicated if you want to analyze them in terms of invariances. But still, we can make classifications of objects in terms of which of invariances they fulfill. That's object. Third category is action. Now I will show you a very short movie, or a movie at least. Maybe you can see what this black pattern is already, black and white pattern is. But if I give you, say, 300 milliseconds, you immediately see that this is a person walking. Sorry, let me go back and I show a little bit more. So here you only see parts of the body, and this movie fulfills the rigidity principle because the marks they are put on the joints of the body. So between these marks, the distances are constant in time. But this is an experiment from the school of Gunnar Johansson. Actually, it's done by a former PhD student of mine, Paul Hemmeren. And the point is that we immediately see that what this person is doing. It takes a couple of hundred milliseconds to identify that's a person and what is the action. And the point of this movie is that we see very little about the object. We don't really see the size. We don't see anything about the shape. We see a little bit about the shape. Nothing about the color. Nothing about the weight. I mean, there is very limited information. But we still identify the action. So my point about this is that in order to identify an action, it's sufficient to identify the underlying force patterns. Runesson, who was a student of Johansson, actually said kinematics, but I put in the force pattern here. I think our brains are good Newtonians, and we pick out the second derivative of these positions of the person. So we identify the forces underlying these movements. So that means I want to characterize actions in terms of force patterns. That is, I give up space, I give up the properties of objects, or most of them at least, and then I focus on force patterns and invariances of force patterns for identifying actions. Now we bring in time. Actions are still invariant under translations and rotations. they are dynamic processes. You need a temporal dimension here. Of course, you can move an action in time, and that's still the same action, but that's a different story. Some inspiration you can take from David Moore again. I mean, he has a paper with Lucia Weiner where they said that these hierarchical representations of objects, like a human being here, we can analyze actions in terms of the differential inequalities of the body parts. I want to go a little bit further and say that we don't only need the first derivative, that we should go for the second derivative of these movements, and that's what's necessary for categorizing an action. I already said this, that it's invariant of all location. It's also invariant of object. I mean, you can have a hand throwing something, but you can also have a machine throwing something. It's the kind of force pattern that is, a hand can be waving, a tree can be waving its branches. It's the movements that are swinging and so on. You have lots of actions are independent of who or what is doing it. It's the force pattern that identifies the object. So these are the three categories. And to some extent, the brain is prepared for picking up these categories. It's well known that the visual information hits the occipital lobe, and then it's analyzed. You add contours, you add the directions, and so on. But at some stage, it's divided onto one direction of analysis where you identify objects, and that's what's called the ventral pathway here, and it ends up in the temporal lobe where we categorize objects. So object categories are identified in the temporal lobes, and the other pathway is the dorsal pathway, where both the where idea, that is the space locations, are identified, but also the how, the movements are also handled by the dorsal pathway. Now, these pathways exist in the brain, and I guess already at the birth of an infant, but you still have to learn the invariances. If your eyes change, if your body parts change, you have to learn new invariances. I mean, if you get a new set of glasses, you have to relearn the mappings. The most extreme case is if you get goggles that turn the world upside down. After a while, you can learn to act in it still. I mean, that's you're changing the mappings. Okay, that's not so much about changing which invariances of all, but more about how they work. So I'm in this respect, I'm an innatist, that the brain has some prepared structure for picking up these categories, the what, the where, and the how categories. That is the object, the space, and the action categories. But it's not totally prepared. We have to learn the invariances as we grow up. We have to learn to coordinate our vision with our hands, for instance. So this is to continue on my critique or criticism of Spelke and Carey. So I have gone through these three categories in rather quickly, since I've already written about them. Now I want to turn to I'm sorry, I have one more thing to say. They are now I go back to the notion of fungibility again, and these are fairly trivial observations that the invariances I picked out to characterize the three categories are such that they can be characterized independently of the other two categories. So we can describe space without objects and actions. We can change the objects and actions, and space remains the same. So the space, actions and objects are fungible with respect to space. And similarly, objects can be characterized independently of actions and space. And finally, actions can be characterized independently. So somehow our brain has learned to separate these three categories into a separate set of invariances. that's a way of partitioning the universe. It's a kind of metaphysical solution to how what exists in the world. But I think we can get some understanding of these three categories by looking at their invariances. So that's a summary of the three first categories. And there is empirical support that I form independent primary categories. One additional source, I mean, this is not a source, but this is a consequence of these categories being fundamental, is that they show up in the structure of language. I mean, almost all languages have nouns representing objects, they have verbs representing actions, they have prepositions, or in some cases they have cases that represent spatial relations in general, not spatial locations. Prepositions are to express spatial relations. So language mirrors to a large extent the fundamental components of a language, mirrors these three basic categories. That's some kind of indirect support for the idea that these categories are really fundamental for our cognition. So now the fourth category, and maybe the category that you as mathematical people would be most interested in. And I should say that this is ongoing work with Paula Kinnon. Now, for one thing, when it comes to number, this is definitely not an innate capacity. There are cultures where they don't talk about number, and at least I can't count very far. And this is the number concept is something that we learn. So this is definitely not an innate category. I want to introduce the notion of a collection, and that some philosophers have worked with this. Some people, Peter Simons is one of the main persons in this area, and he calls it manifolds or sometimes multitudes. Even Husserl talked about collection, and he called them Zusammenfassungen. Don't worry about the terminology here, but I use the word collection. And a colleague of mine, Ingvar Johansson, he's also been interested. He worked with Peter Simons. He says that a set is more than the sum of its elements, and a melodical fusion is a sum. But a multitude, he uses the word multitude. A collection is simply its members. And he also says that the collection is something that is completely stripped of all relations between the objects that make it up. And then another colleague of mine, former colleague, Sophie Angere, wrote a paper where she argues that collections are not the same as sets. And her example is that if you have these four objects, you can group them in two ways, either these two together or these two pairs together, and then you can put all four together. And if you do this in set theory, you can get two sets here, a set consisting of these two sets or a set consisting of these two sets. And in set theory, they are not identical. But as a collection, this is only consisting of the objects. There is no partitioning into substructures as you find in set theory. So collections are not sets. And Sophia Anger axiomatizes collections. I don't want to give you the axioms because they are a bit difficult to explain. But she derives a theorem saying that the set of collection forms a complete atomic Boolean algebra. And we basically take out all objects and then you put them to two sets of all the collections of all objects, so two objects and the three objects and so on, and then you get a atomic Boolean algebra. I assume, just to make things simple here, that we only work with finite collections of objects, even of physical objects. This is an assumption we can discuss if you like, but in order not to make things complicated, I assume that we only work with finite collections. And another assumption of this school with Peter Simons and Ingvar Johansson is to say that the number concept is a property of a collection. So in other areas of mathematical philosophy, numbers are considered in a different way. But I want to follow this tradition and say that a number is really a property of a collection. And I will try to explain that in a while right now by giving you examples of properties of collections. So some of the properties of collections, they are shared with properties of single objects. So a collection can have weight, like in these carrots weigh 1 kilo. They can have a location, the olives are in the glass can in the cupboard, or they can have a temperature, and they can have a color, and so on. They can have lots of object properties. So some of the properties of collections are shared with other types of objects. But there are properties of collections that are unique to collections. A collection can be ordered or it can be unordered. An object cannot be ordered. A collection can be dense or it can be spread out. An object cannot be dense. Well, it can be dense, but I mean, an object cannot be spread out at least. And a collection can be uniform. It can contain the same type of things, or it can be mixed. It can contain different types of objects. So there are properties of collections that are unique to collections. And then there are a couple of what we can call numerosity properties. Not very many, but I give you some examples there. An object can, a collection can contain few objects, it can contain many objects, it can contain 5 or 4 and so on, an exact number property. So these are special property when we talk about numerosity. And then a very important property of collections here is that they are invariant of the spatial location. If I take a bunch of marbles and I move it around and I place them in different places, and whatever I do it to them, they still form the same collection. Okay, normally we think of a collection as something being at the same place, but it doesn't have to be so. You can have an art collection that is distributed over the world or whatever. But what we identify as a collection is invariant of the spatial location of their elements. That's one of the fundamental invariances of collections. And then we can take the Piaget's experiment with young children. I've forgotten the age of the children, but young children, I think they were 2 and 3 year olds. They were shown a number of pieces of candy like this in a row, and then you spread them out, and then you ask the child, in which row is there more candies? And small children will say that there is more candies in this row because it takes a larger place. But older children will say that there are the same number in both. There's the same amount of candy in both of these groups or these collections here. So Piaget shows that this idea of collections being invariant of the spatial location, this is not inborn, but this is something we have to learn, that this is the same collection, even if we spread out the objects. We have different concepts of numerosity, I should say. We have something called a magnitude. That's not number, it's a large bag of beans. A small bag, large is magnitude. You have numerosity like few and many, and then you have number, which is precise. So there are different ways of expressing numerosity, magnitude. I don't know what is the right word, covering word for all these 3 types. And the numerosity forms studied as a separate brain in the separate system in the brain. It's called the approximate number system. And Stanislas Dehaene has studied how we perceive these approximate numbers. And animals can handle approximate numbers, but they cannot handle number when you get above very few items. So having a number system that extends beyond 3 or 4 is unique to humans. So that's, and now I want to talk about the number property, the property of number that applies to collections. And now we get back to fungibility again. So here is a definition. A property of a collection is fungible. When a collection that has a property, has this property, when you replace it by another one, I mean, at the same place, the resulting collection also has property P. So an example is, spread out is a fungible property, because if you have a spread out collection, you take away one object and replace it with another object. The collection will still be spread out. And an order is the same. If you have an ordered collection, take away one object, replace it with another one, the collection will still be ordered. So these are two examples of fungible properties. And of course, number is fungible. If you take away an object and replace it with another, the number of the collection will still be the same. You can make this notion of fungibility a little bit more precise, or a little bit more divided into subclasses. So I have divided it into identity fungibility, where the replacement is done with an identical object. So okay. There are lots of experiments on children and on how they learn to count. And in these experiments, I mean, I told you about Piaget's experiments with moving things around, or you do different things to the collection you have in front of the child. But I would say 99% of the experiments, they are all involving identical objects. And I think that's a little bit of a shortcoming of the studies of children and how they learn number, because you would learn more about how they understand number if you had different types of objects. So yeah, okay, uniform is an identity fungible property of collections. But then you can have fungibility of objects that belong to the same category. So if you have one object, you replace it with another object, doesn't look the same, but it's the same category, then it still has the property. So uniform, I mean, if you have a set of what should I say, blue blocks, blue Lego blocks, and then you replace one of the blue Lego blocks with a red one, then it's not the same category. It's the same category, but then it's not uniform anymore. So uniformity is not fungibility with the same category. But let's take being a herd of cows. That's a category fungible property. If you have a brown cow in a herd is replaced by a black and white cow, it will still be a herd of cows because you replace it with a cow. If you replace it with a horse, then it's not a herd of cows anymore. So uniform, as I said, is not a category fungible property. And then finally, you have fungibility of arbitrary objects. And you replace any object with an arbitrary object, and if it still has the property, then it's fungible, arbitrarily fungible. So number is an arbitrarily fungible property. So that's my analysis of different levels of fungibility here. And number comes out as well, I'm not certain it's the only property, but anyway, let's see what happens now. A little bit of a side remark. In my work on natural concepts or concept learning, concept formation, I have argued that natural properties are convex. I mean, I'm assuming that we have spaces of objects and so on. I don't want to get into the details here, but I mean, I've played around with this idea that convexity is a very natural property, property of properties. And here is a little bit of a foul trick, but anyway, I want to show that the number property can be defined using the convexity of number properties can be identified if we use fungibility here. So let's say that a collection is a neighbor of another collection if it arises by replacing one object in the collection. And then we can talk about path between collections if we can reach it via a series of neighbor steps. And then you can introduce this notion of betweenness that is crucial for convexity. And you talk about the shortest path between two collections. And then you say that something is between, collection Z is between X and Y if it lies on the shortest path between X and Y. If you do that, you can show that having the number property n being 5 and so on is a convex property. This is a little bit of a mathematical trick, and I don't want to put too much emphasis on it. But still, using fungibility, you can find some notion of convexity that you can apply to the number property. I mean, it's a fairly trivial thing. It doesn't give you much mileage, but anyway, I've done it now. Now we get into my more or less concluding idea here, and that is simply to say that the number property is determined by two things: spatial invariance and the fungibility, the arbitrarily fungible. They determine the number property. And a very simple observation is that two finite collections can be matched by a part of arbitrarily fungible exchanges if and only if there exists a one-to-one mapping between them. So in math, we talk about two things having the same numerosity, having the same number, if there is a one-to-one mapping. And we can replace that notion of one-to-one mapping by fungibility. The proof is simple. I mean, it's trivial. It's term of induction. It's inductive proof, but it's a very trivial proof of this. But my point here is that we can I shouldn't say get rid of, but we can replace this idea of one-to-one mapping with fungibility. That's the only point of this observation. And then it follows that two finite collections have the same number property. They both belong to the number 6 or the number 8 and so on, if one collection can be transformed into the other by a series of replacements of arbitrary objects. So this is an identity criteria for the number property. And since collections are defined as being independent of their spatial locations, they are defined by the spatial invariance, and number applies to collections. If you put these two invariances together, we get, I think, I mean, this is more or less a hypothesis so far, that the number properties are then determined by these two invariances under location and being an arbitrarily fungible property. So this is, mathematically, this is quite trivial. But what I've done here is to use some kinds of invariances. I mean, the invariance under location, which is a fairly trivial one, but it's something that we learn. And then we learn in order to identify the concept of the collection. And then this notion of fungibility, which I use to replace the notion of one-to-one mapping. Now, going back to experiments with children, as I said, there are lots of experiments with children. I haven't, or me and Paula have not been able to find a single experiment where we test these fungibility properties. There are maybe something when it comes to this identity replacement, but there are very few, if any, experiments where they test these arbitrarily fungible properties. And it would be interesting to see when children understand that if you do this arbitrary exchange of objects, that the collection still has the same number. At what age they understand that, or they can use that in their understanding of numbers. So we lack a little bit of empirical underpinning for understanding how children learn the number concept if you analyze it in this way. So this ends my talk. I've given you a brief summary of why we sort the world in space, object, and action, and what kinds of invariances we use to identify these categories. And then I extended it to the number property by introducing two other types of invariances that we use here. But as I said, this is a culturally learned property to understand the number of a set or a collection of objects. So thank you very much for listening.